Greetings everyone, my name is Jakarta. Today I'm going to present our research. The topic is about monitoring land subsidence induced by the groundwater change using Sentinel 1 and gray satellite observation over Jakarta capital city, Indonesia. So the outline of this presentation consists of 5 parts, ranging from introduction part until the conclusion part here. First is the previous studies of InSAR measurement over Jakarta capital city. Here, we do have like 5 different previous studies over Jakarta capital city, but they have like major limitation as I have listed here, ranging from number 1, which is no validation with ground measurement, until the small number of image pairs they use to perform the interferometric measurement. So that's why here stands our research that's focus on overcome those limitations. So in terms of the study area, here show the figure the extent of our study area covered in reflectivity map along with the distribution of GPS station used to validate the InSAR measurement, which is one station of CJKT here. So the research objective is to precisely monitor land subsidence and groundwater change through InSAR and satellite gravimetry observations. And several things to consider in this study is that it's ranging from number 1 to number 6 here, which is to validate with the ground measurement as well as to understand the groundwater perspective through the gray satellite observation. Now in terms of the dataset used, here we use the Sentinel 1A imagery, which is in descending orbit, consists of 94 SLC image from the initial launch from November 2014 until December 2019, and later we use the SRTM 3 second as the reference DEM. Now in terms of the ground observation, we use the GPS station. It has the daily measurement in 3 displacement components from north, east, and east direction, and later we project it into line of sight direction for the validation purpose. And here show the photos of the GPS station we used to validate the InSAR measurement. Now, for the groundwater perspective, we use the Global Land Data Simulation System or GLDAS version 2.2. It has the daily temporal resolution with 30 km spatial resolution as well. Now, for the InSAR measurement techniques, first is the InSAR. The main concept is that we use the consecutive master and select image to optimize the temporal baseline here. In terms of phase removal, we do remove the phase from topography, flat earth, and the orbital error. Next is the empty InSAR. Here we use the single master image to optimize the spatial baseline, and later we remove the phase from topography, flat earth, and the orbital error as well. Lastly, for PS InSAR, we also use the single master image, but in terms of the phase removal, additionally, we also remove the phase not only from the topography, flat earth, and orbital error, but we also remove the phase from the atmosphere. So that's why we utilize the Amplitude Stability Index or ASI for atmospheric phase screen, APS, and PS point selection. The formula to calculate the ASI is shown here, so we consider both standard deviation and mean amplitude of the whole SLC image we use, so the value of ASI will be relative to the number of pairs we use. Now, in terms of the gray TWS to GWS concept, here the total water storage anomaly, which is originally measured from the gray satellite, it consists of different water components in Earth system. So if we subtract the TWS with other water components such as water from soil moisture, from surface water, as well as from snow, we can finally derive the groundwater product. So following this concept, it is possible to derive the groundwater anomaly, storage anomaly from grays from this assimilation process once the other components of TWF have been identified individually. Now, while we consider the line of sight projection, here in the left-hand side figure, we see that the native-looking SAR sensor cannot really distinguish the scattering, the object located in A and B here. So to overcome this issue, we designed the SAR sensor as side-looking, So we can distinguish the object in A and B here. Because of that, what SAR measure will not be equal to GPS measure. So to make sure that those two are in the same projection, we project the GPS data into the SAR perspective using this equation. By considering the satellite incident angle as well as its heating angle here, and the three displacement components measured by the GPS. Now, for the result part, here show the graph show the overall value of InSAR, GPS, and grace measurement. For both GPS and grace measurement, we can see that both have the similar trend, which is declining trend throughout the whole period. But in terms of D-InSAR and MT-InSAR, we see that they don't have a clear trend here, and they don't really agree well with the GPS and the grace measurement. But on contrary, as for the GPS InSAR result, it seems to have a similar trend or similar pattern with the GPS measurement as well as with the grace measurement, which is declining trend over time. So later, in terms of the accuracy and agreement measurement, in this table, we can clearly see that PS InSAR has the highest agreement as well as the lowest error recorded in the root mean square error in centimeter unit. And for the agreement of InSAR measurement with the grace or groundwater perspective, the PS InSAR also has the highest agreement compared with the other two techniques. Now, for the discussion part is the increasing global water vapor. Here, the research from the Chen and Liu recorded that there's been an increasing global water vapor content in troposphere, which might cause the microwave signal to be delayed. This kind of delay will make the error measurement for surface deformation purpose up to 10 to 14 centimeter errors. So that's why this kind of issue will make the InSAR measurement is getting more challenging to conduct, especially in the tropical region. Now for the PS InSAR perspective, theoretically, a pixel with an amplitude value from 0.25 to 0.4 can be selected as PS point if composed at least from 25 SAR image. Well, in our case, we have yet to reach millimeter accuracy, although we have used higher threshold, which is 0.8, and more SAR image pair, which is 94. And another atmospheric phase screen or APS approach could be considered, such as using external data from high-resolution meteorological models, MODIS or MERIS data. Lastly, for the groundwater perspective, the InSAR measurement could be combined with GRACE groundwater storage anomaly product to better understand the potential cost of land subsidence over the study area. And the newly published of GLDAS version 2.2 has assimilated with GRACE total water storage product into the GWS with significant increase of its spatial resolution from 400 km to 30 km and the temporary resolution as well from monthly to daily resolution. Now from the conclusion part, it is important to consider applying the atmospheric phase screen or APS to ensure the precision of InSAR measurement, especially in the tropical region where the water vapor content at its peak. And the satellite gravimetry product of groundwater storage anomaly measured from the GRACE satellite, assimilated with the GLDAS version 2.2, could also be incorporated with InSAR measurement to understand the potential cause of land subsidence. And lastly, the potential future investigation could be conducted such as applying different parameters for PS selection, using external weather data to perform APS, or using continuous wavelet transform or CWT to check the agreement between InSAR measurement versus GPS measurement from the ground measurement. So that's pretty much of my presentation today. Thanks for your attention.